Isomerism and organic chemistry. C3H7NO is a molecular formula with only 12 atoms. It's incredibly simple, but it can form over 60 isomers. Today, we will be looking at the C3H7NO as a tertiary amide, as an enantiomer, and as an unstable molecule. So, investigating C3H7NO as a tertiary amide, we must first draw the structure. And in order to do this, we have to calculate the number of double bond equivalents. We can do this using the formula C minus number of hydrogens divided by 2 plus number of nitrogens divided by 2 plus 1. Now, if we substitute in the values from our C3H7NO molecule, we get this equation, which is equal to 1. That means that our molecule must have either a double bond or a ring. So before we draw our line structure, we should list out all of the information we know. From the previous slide, we calculated that our molecule must have either a double bond or a ring. We also know that it must have an amide functional group, and we know that the amide must be tertiary. The C double bond O that is necessary to create the amide functional group satisfies our need for a double bond, so we know that it will not have a ring structure. We can start drawing our molecule by putting in an amide functional group. Now we know that the amide must be tertiary, so we can add the methyl groups to the nitrogen. And finally, to saturate the molecule fully, we can add a hydrogen, and our line structure is complete. And that would be called NN-dimethyl methamide. Enantiomers are optical isomers of the same molecule. While these molecules have the same structure, they cannot be superimposed on each other. Optical isomers are essentially mirror images of each other. Now we can see some potential optical isomers of C3H7NO. We know that it must be a ring structure, because generally optical isomers require 4 different groups around the chiral carbon in the center, and we already calculated that the double bond equivalence is 1, so it must have a ring structure. Now, how would we name this molecule? To name this molecule, we can follow the IUPAC's helpful guide on systematic naming. First, again, we should list what we can see about the molecule. We know that the molecule has a cyclic structure containing 3 atoms. We also know that within the ring there is an oxygen atom and a nitrogen atom. And finally, we can see that there are 2 methyl groups. So to name this molecule, we would start by listing the methyl groups and their positions. So there's one methyl group on nitrogen and another on the 3rd position. So it would be N3-dimethyl. Now we must list the oxygen and the nitrogen. So 1 oxa, 2 aza, listing where the oxygen and the nitrogen are in the ring, the oxygen taking the position 1 over the nitrogen as it has priority, and finally finishing the molecule with cyclopropane. We can also give it a name that is more standard and is the preferred name by the IUPAC over the systematic name of N3-dimethyl oxaziridine. Now, to specify the enantiomers, we must assign priorities. So, oxygen has the highest priority, followed by nitrogen, followed by carbon, followed by hydrogen. To begin, we must face the molecule in a position where hydrogen is facing away from us. And as you can see, in each case, hydrogen is already facing into the plane and away from us. Now, if we follow the priorities around the molecule, we will see that it will either go anti-clockwise from oxygen to nitrogen to carbon, or it will go clockwise from oxygen to nitrogen to carbon. And these dictate the naming of the molecule. If it's clockwise, you will have the R isomer, and anti-clockwise, you will have the S isomer. And as you can see with the molecule, with this one, we are going clockwise, and we'll have the R isomer. And with the other one, we are going anti-clockwise, and we'll have the S isomer. The final branch of this topic that we will be talking about is stability within the molecule. Now, different isomers will have different stabilities, but this particular isomer that we have just looked at, the N3-dimethyl-1-oxo-2-aza-cyclopropane in either the R or the S form, is a highly unstable molecule, one of the least stable isomers in fact. And this could be for two main reasons. The first is due to ring strain. The 4 valences on the carbon atom want to form a tetrahedral shape. However, this is disallowed by the ring structure. Being an equilateral triangle, it will have a roughly 60-degree angle. And this can be said for nitrogen and oxygen as well. Of course, nitrogen looks to find a 107-degree angle and has a 60-degree angle too, and oxygen is looking for a 104.5-degree angle and also has a 60-degree angle. Now, the reason that this may be unstable is because of the large difference between the angle that the atom wants to have and the angle that it has in actuality. It is being forced closer together, and this puts strain on the ring. Another reason that we might see instability in the molecule is due to the heterocyclic nature of the ring. The ring contains both oxygen and nitrogen, and the bond between oxygen and nitrogen is far less strong than the bond between carbon and carbon. As you can see, the bond enthalpy is 201 in the case of the NO bond, and in the case of the CC bond, it is 347. Obviously much greater, which leads to a higher stability. A lower stability in the case of the molecule we are looking at, C3H7NO. Thank you for watching this presentation. I hope it has been very informative and enjoyable for you as a listener. As you can see, the references are here if you would like to do any further reading into this subject. Thank you.